This example illustrates the difference between an interval of validity and the existence uniqueness theorem and what they say and how they're different. So this isn't such a bad ordinary difference equation, and we've actually seen it a lot of times before. It's also an instance of the logistic equation. So not that bad, it ends up being 3y minus y squared. Doesn't look so bad. And we're given an initial condition here, y at x naught equals y naught. So if we were to apply the existence and uniqueness to this thing, we get f of x comma y, and partial f partial y, they're continuous everywhere. Doesn't matter what x is, doesn't matter what y is. So the solution exists and is unique near, and that's the really key thing about the existence and uniqueness theorem, near the initial condition x naught, y naught. That's all we're guaranteed. It doesn't have to exist in unique far away, it just will exist in unique near it. But you are guaranteed that no matter what point you pick, you'll have a solution that exists and is unique nearby that point. So this one is a little interesting. It ends up having three separate solutions that don't quite fit into the general one. So we have y equals 0 as one solution, y equals 3 is another, and then y of x equals 3 times e to the x over a constant plus e to the 3x. And if you draw a direction field and you plot that stuff out, it ends up looking something like this. And in the past, we've always looked at, okay, well, if you start below the x-axis, then you just keep going down and down and down. If you start above 3, you just get closer and closer to y equals 3. In the middle, we just, if we're a little bit above 0, we'll end up getting closer and closer to 3. So this region, that's what it acts like, but what actually happens if you keep going forward in time here, in this bottom region, when y is less than 0? So let's take a look. If we have an initial condition y of 0 equals -1, that ends up having solution y of x is equal to 3e to the 3x over -4 plus e to the 3x, excuse me. Right, and that does seem to work out. If we plug in 0 for x, we end up with 3 times e to the 0, so we have a 3 on top. And then we have -4 plus 1. So 3 over -3 is -1, so it works out. So then we're starting this out here, and I guess I'll do both. All right, let's see. X, y, and this point here is -1, and that's where we're starting. But now something interesting will happen. So eventually, right, we have this -4 on the bottom, and we have e to the 3x. E to the 3x is going to keep getting bigger, and eventually e to the 3x is going to be 4. And so on there, what if I set, -4, excuse me, -4 plus e to the 3x equals 0. Well, that's e to the 3x is going to equal +4. Take a natural log, we get 3x equals natural log of 4. So x equals 1/3 natural log of 4 is when the denominator will actually become 0. And so that's about a third. To give myself room, I'm just going to put it in someplace. This isn't to scale, but here we go. We've got 1/3 natural log of 4. So you actually have a vertical asymptote right here for this particular solution. The vertical asymptote changes based on where you start. It moves over, but this thing will end up actually doing that. It'll go down. Let me try and draw it a little better. It'll go down to -infinity. So when x becomes 1/3 natural log of 4, the bottom becomes 0, and you get, as x is getting bigger and bigger, we get -4 minus a number that's plus a number that's a little bit bigger, a little bit smaller than +4. This number it's negative, but it gets closer and closer to 0. The whole thing gets super duper negative because we have a reasonable number on top and almost 0, slightly -0 on the bottom. And then what's going to happen is it's going to have, and I'll have, let's see, that's 3. It's going to start back up over here. And this thing, let me just put in my dashed line, then this thing will asymptote to the 3 solution. So actually the interval of validity for a particular solution of this is going to depend on both x naught and y naught. And it's because of this vertical, this thing goes to infinity. negative infinity in a finite amount of time, and ends up coming back up there. And it's going to change based on every single x naught and y naught that you pick. So in this case, for y of 0 equals -1, the interval validity validity it's negative infinity. We can keep going backwards in time. I think that'll happen. Negative infinity to 1/3 natural log of 4. Let me go ahead and steal that. And so a similar thing will happen if you start at a point up here. I'm not going to solve for it because it's going to get pretty nasty. But if instead I had, let me try and redraw that. So that's going to give me enough room, I think. That'll be 3. If I had a point that I chose right here, if I go forward in time, it's going to work out. So its interval of validity would be up to positive infinity. It's a terrible infinity. There we go. But then eventually, it's going to, if you run backwards in time, it's going to do the same thing this did, and it's going to jump up to an infinite value. It's going to have a division by 0. And then if you go down, this one then would kind of go back and it would do that. And so if we called this A, then it would be from A up to positive infinity if we started at this initial condition, if this was our x naught, y naught. All right, so now kind of to consolidate, to make sense of what the existence uniqueness theorem says and what the interval of validity is saying, the existence and uniqueness theorem doesn't tell you how long the solution exists. It just tells you that if f and partial f partial y are continuous in a region that contains your initial condition, an open region, then you'll have a solution around the point, at least for a little while. You don't know how big that while is, but you'll have a solution around it. But you're not guaranteed that it's going to exist if you keep going backwards in x, or if you keep going forwards in x, or if you keep going up or down in y. So it's very limited. You just know there is a solution, and it exists at least for a little bit while around that point. Exists and is unique. And here's kind of an example of, it has a problem if you start either going forward in time, if your initial condition is y of 0 equals -1, or if you go backwards in time from some initial condition that starts above y equals 3. So kind of very fine detail there. You have to read these theorems very carefully, what they guarantee. So you're not guaranteed the solution exists forever, everywhere. As long as you don't cross a discontinuity, you're just guaranteed there is going to be a solution for some neighborhood around the initial condition.